Very nice.
Sorry.
Means being transcribed. Transcribed.
That's like a weekly meeting.
Oh, grand. I made that.
I hadn't seen that until last night.
Oh, really? Very funny. Well done. Well done. Oh my God. Alleyway was alleyway. Okay, but that was actually, that's me. That's
It
it.
does look a little bit. So now the potato and the sweet potato.
For using our account.
Well, that's the numbers are.
So you're, who are we looking at?
I don't think that they'll. I can promote them to analyze so they count them as they.
Use like a different.
So Brent, this is how down there.
Yeah, you got it's being able to sit myself, Jerry. Oh, you were going to be just like, you got because you really nothing. Plug it in with my jump clips. I'll plug it in.
Maybe we should let maybe 10 minutes. So
How are you? They might be in the room
2, and there might be people online that have another meeting at 2 o'clock. So if everyone can find a seat, I am really happy to present Josh for his dissertation defense. I feel like he's getting married and leaving me forever. And I want, for people who are online, like, this is not Josh's title slide. This is just something I prepared. A little bit about Josh. He got his BS at the College of William and Mary in 2018. He works with Matt Kerwin, which maybe many people have heard about or worked with before. Matt's a great guy. The stroller went down here and then I got it's really uncommon for someone to publish their undergraduate honors thesis. Josh did that. Yay! Josh. So after he went to William and Mary, then he went to the Peace Corps for a year, and that got cut short. And he came back early in December and like reached out to me from Liberia, wanted to come to UNC perhaps. I was like, yeah, maybe. He shows up, and this is March of 2020, and right before COVID hit, and this is our recruiting trip. And so you can see Josh here in the middle next to Tyler, someone who's graduated a while ago. Freezing trip. And that's when I knew I wanted to work with Josh. And I was so happy that he wanted to work with us. He came that summer before. We're all wearing masks. We wanted to look at the distribution of oyster shells on reefs. And we had all these great ways that we thought we could track individual shells. Nothing worked out. So you're not going to hear anything about this today. But then we did see some salt marsh, and I think that was the inspiration for what you're going to hear later. Josh he helps out everyone. He builds community wherever he is. He's built tremendous community here at IMS and on campus, and that's something we all appreciate. He's an excellent cook. He made this dish for me. It's a Liberian fish stew. And if you look closely, he gave me the piece with the fish head in it, and that was out of respect.
I was hoping you would show this. Yeah.
He's worked with lots of undergrads. He's been here a while, but mostly it's because we didn't want him to leave. So he's been here for 6 years, but he's worked with lots of undergrads during that time. He even helped me get Molly married. So we were the witnesses, and you can see how happy they are. So right after, and then a few minutes later, walking to the waterfront, that's Molly and Ryan. And with COVID and my job changed, I didn't get to go to too many meetings with Josh, but we did get to go to one recently, and it was a lot of fun, and these are just some pictures. And I just want to say, I know you're going to do great today, and We're really gonna miss you.
Thanks. All right.
All right,
Nice.
enough of that. Let me stop sharing.
I'm going to plug in and see if this computer connects.
Oh,
Okay, have we
nice.
seen that? Nice. Wow. Well, thanks, Tony, for that introduction. That was incredibly kind. I didn't know you were going to put together all these photos. That was lovely. So my dissertation today is titled Depositional Connectivity Across Temporal Scales in Marsh and Barrier Island Systems. And so thank all of you for coming as well. A lot of familiar faces here. And to folks online, I'm going to try my best to use the digital laser pointer so that you can see what I'm just gesticulating towards here on screen, but I think it also works in person. And I'm excited that Aviva here is here as well, who I think is the youngest scientist in the room at 2.5, though she's left, but she'll come back. So I want us to first start by imagining that we're migratory birds coming down from the mountains of the Appalachians for the first time. And we're met with a landscape like this, where as far as the eye can see, things are flat, there's expansive marshes, there's a forest in the background, but it's pretty shallow. Things just look flat. And that's where we are. Maybe in the distance, you'll notice a bridge. That's about the tallest thing we have. The tallest elevation in our county is probably made up from one of these bridges that crosses over the water. And so as a migratory bird or as a drone flying, you just you might realize how flat this landscape is. And that's because we're in the coastal plain of North Carolina. So this is an area that's fed by sand and mud and clay coming down the rivers from the mountains. And none of that material is consolidated. It's all loose material held together by vegetation, by the dunes of the barrier islands and the grasses of the salt marsh. And so it's sort of at the whims of a variety of forcings. So barrier islands here are most susceptible to storms, which on the timescales of hours to days can reshape these islands, eroding them and moving sand around. But behind these barrier islands are the salt marshes, these fine grained systems that are protected and also are reshaped on short timescales, but also via the tides being flooded twice a day during high tide events. There's fluctuations daily, but also monthly tidal ranges. And then there's sea level rise, which is sort of the force that is shaping our coastal plain on geologic timescales. And to see just how dynamic this sediment-laden landscape is, I've included a satellite record from 1984 to 2015 of Cape Lookout. And here we see the island growing by kilometers at a time and a spit trying to refuse back with Shackleford banks. And so this is a really dynamic landscape, especially for the people who live on it and depend on this area as a place of commerce and home. But we're not the only people who are on a coast. 1 billion folks worldwide live within 10 kilometers of the coast, and that number goes up to 3 billion within the first 100 kilometers. These numbers have also grown. So Rodriguez et al. Showed that from 1950 to 2010, in green here, there's been massive population growth in coastal areas of the United States, but that trend is also similar globally. If we want to put a dollar sign on wetland defense from things like marshes and barrier islands, that number is around 450 billion as of the most recent estimate globally. And so these are valuable, in protecting our coastal infrastructure. And then 10% of our global coastline is fronted by barrier islands. So in the United States, on the East Coast and the Gulf, these pink areas are all barrier island protected coasts. And marshes are also similarly globally distributed. In red here shows the 1.7 million hectares of salt marsh that exist in the world, and that's about twice the size of Massachusetts. And in North Carolina, we have 220,000 of those hectares in this low-lying, expansive coastal plain. So a lot of the marsh is right around us. And 90%, so this is, I think, for the biologists in the room who are like, why do we care about the geology? Well, 90% of our commercially important fish and shellfish in North Carolina depend on wetlands at some point in their lifetime. And these wetlands, the coastal marshes, are the #1 highest modern sequesterers, or among the highest carbon drawdown ecosystems on planet Earth. But all of these ecosystem services depend on the capacity of these marshes and barrier islands to keep up with sea level rise. And here, the NOAA sea level rise viewer shows 4 feet of water level rise by 2100, and areas that were once upland turning into marsh in pink, and then eventually being drowned by water. But this estimate is simply a bathtub where we fill in the ocean with water, forgetting that we're on a dynamic landscape where sand can move around, the coast can reshape sort of at the whims of storms and sea level rise. And part of my dissertation, a big thrust of it, is to understand how the marshes and barrier islands might respond in a way that's distinct from the sea level rise story, where we might actually see marshes surviving in some areas, but not in others. So the way I plan to do that today is by using 3 chapters. Briefly, I'll talk about barrier islands, and then I'll move into work on salt marshes, where I explored accretionary levees, these features that exist at the edge of the marsh, and looked at their capacity to moderate suspended sediment gradients across the marsh platform, and also to maybe moderate resilience of these 220,000 hectares of marsh that we have. So to jump into the barrier island chapter, which I'll only present here for this one slide, we looked at a variety of barrier islands. Here I'm showing North Core Banks, which is about 50 kilometers from us. This was published last year in JGR Earth Surface under the title of Washout versus Washover, Distinct Trajectories of Barrier Island Reshaping. And one of those features, or one of those trajectories, is washover, which brings sand from the ocean's shores and from the beach over the island through the dunes and into the back barrier, building elevation of a barrier island. And so we used a variety of drone mapping and LiDAR mapping to define the elevational recovery of these features after they form and how quickly they form, and then related that to both modeled and measured water levels. So this is washover. This helps facilitate landward migration of barrier islands with time. This generally is helpful for these barrier islands to persist. But washout, on the other hand, and this is sort of a newly identified phenomenon, or newly studied, carves the island directly the opposite way. And this happens when water levels in the sound, which exists behind these barrier islands, surge out during a storm to the ocean. And with that energy, finding any low point in the dunes, they scour a lot of the barrier island and send it offshore. So this directly offsets the migration that we see with washover. And so we believe that this could be integrated into transgression models that try to predict when barrier islands will drown inevitably and open up the marshes behind them. These are the outer banks, when they might open up the inner banks to more erosion. And so those inner banks are where I'll move for the rest of the talk. These are the marshes that make up the coastlines more or directly adjacent to us here. So these are the inner bank marshes, where we have expansive low-lying plains of marsh fringing the upland area with forests. And there's these small rivers that meander through the marshes and feed out into the open estuary, carrying sediment and nutrients that are nourishing the marshes if they can reach the interiors. And again, just to orient you to how much of this marsh we have in North Carolina, all that purple area is the marsh. And luckily, these marshes aren't static. We know it's sediment that can move around, and they have a capacity to migrate both upland, horizontally, and vertically in place. So at some lower sea level, the marsh might look like this. And as sea level rises, we see the marsh pushing upland, this wedge on top of the old wedge, and the forest dying off. And we also see vertical accretion in place. And this vertical accretion depends on in-situ vegetation growth, so plants successionally growing on top of one another year after year and not decomposing, as well as sediment delivery, which comes from, at high tide, what's in the water column. And it's the sediment delivery story that I'm most excited in as a geologist, because for me, I find these 2 photos equally cute. And I just think that's the smallest marsh core I've ever seen. It's lovely. It's nice. But the sediment story is, let's say it's distinct in some of these watersheds. In very large river basins, we've seen a decline with damming in rivers of sediment supply. So that's the nutrients that that's the material these marshes need to keep up with sea level. So there's been a decline in large river basins. But that ignores the story that we have a lot of landmass still being drained by very small watersheds that directly feed into the coastal plain. So these are our coastal plain rivers on the right here, draining a lot of landmass, and there's many of them. And in these areas, we have proportionally high sediment yields. So for low basin areas, you have a lot of sediment that's coming off the landscape and making it downstream. Here are 12 of those watersheds in North Carolina that our lab group has studied in the past. They're outlined in teal. And these watersheds have been associated with a lot of population swell as folks move towards the coast. And so in these 12 watersheds, 12 of them across the area here, and 10 dates where Boston and others have classified land use in these regions, we see just how drastically landscapes are changing in the past 60 years. This is from 1959 on the left to 2010. And so you might notice a trend of development from right to left in these watersheds. That's sprawl out from Wilmington. And so from 1959 to 2016 there, in this watershed, 75% of the area was cut down and replaced with what's considered developed land use. But there's also silviculture, tree clearing, and agriculture happening in these watersheds. And these drive sediment yields downstream, which have an effect on the subtidal and marsh systems. Here's another Landsat time lapse of deforestation in one of those watersheds, where orange forest is replaced by this green sort of low-lying vegetation. And so I'll show a lot of transects in the rest of this talk that look something like this. They move from A to A prime. So that's the cross-section area we're looking at. And now I'll display them on the top here as a schematic where we have subtidal water areas or the channel. We have a levee, this kind of elevational feature at the edge of the water and marsh interface. And then we have the marsh interior on the right. And so this levee edge features is something that sort of exists and might moderate connectivity between these two adjacent systems. And past studies, like those by Bost et al. In 2023 and 2024, have shown that subtidal areas here are infilling with sediment more rapidly than sea levels are rising. And so we know this by looking at sediment accumulation rates in cores and seeing how fast in millimeters per year that material is building elevation. And then we compare that directly with local sea level rise. And so these subtidal areas where the water is always on top of them are across those 12 watersheds keeping up with sea level rise. But the interior marsh is not. So most of these bars are showing a deficit below zero, where sediment accumulation rates are less than sea level rise. And so if that trend were to continue, these marshes would no longer exist in their current position. They can't keep pace or keep their head above water for long enough. And so we wonder if levees partially explain the depositional disconnect between infilling subtidal regions and marsh interiors which have a deficit. Maybe this elevationally prominent feature at the edge tells part of the story. And maybe these levees are responding distinctly from interiors and often are forgotten in the story. So the first thing we set out to do was take sediment cores in these regions. But before I get there, I'll talk about how levees form in the first place, because they exist in a lot of systems. On subtidal flooding, water spills out, or on tidal flooding, water spills out of the channel here and onto the marsh platform. And as it does so, water velocity slow and sediment that's in the water drops out of the water column because there's reduced capacity and reduced velocities to move that material deep into the marsh. And that's because of generally vegetation and a larger cross-sectional area of flow. So material drops out adjacent to the sediment-laden waters building the levee. And then with sea level rise and no added suspended sediment, we expect that the marsh will just move landward and upward through time. That's marsh migration. Here, with no sediment loading, the profile of the levee looks similar to what it did before, just at a higher position. Now, if we're to add extra sediment into the water column here, we presume that because of the decreasing sediment load across the marsh platform, most of that material will end up towards the edge, building a prominent levee. And this levee then might have the capacity to reduce interior sedimentation for some period, because it can obstruct flow and force water to take more circuitous routes into the marsh. And it also could act sort of as a dam, preventing flow off of the marsh platform. And if water sits on the marsh for too long, plants begin to die off, and we see interior ponding. And because those plants are an important part of the accretion story as well as sediment, these levees might be moderating cross-shore flow. So we ask, how do we track levee emergence and its capacity to disconnect adjacent settings? And there's three methods I'll talk about today. The first is using sediment cores, which allow us to resolve subdecadal changes in sedimentation rates, as well as levee emergence. So we take these cores directly at the edge of the marsh on top of the levee, 8 meters in and 15 meters in from the edge. Then we can look at edge rollover via remote sensing of shoreline erosion. to see how far those shorelines have eroded with time on decadal scales, and also how much additional sediment is coming off of the shoreline from erosion itself, as opposed to the upstream fluvial sourcing from land use change, how much is coming into the watershed just from these shorelines eroding. This is known as marsh cannibalization, where old marsh is eaten by new marsh and deposited directly back onto it. And then finally, we can measure suspended sediment concentrations in situ. So what's in the water column across present day levees. So once levees have risen in height, we can look at a variety of levee morphologies and say, how do they moderate sediment transport in the present day to see if they actually are affecting the resilience of interior marshes or the connectivity between the sediment-laden waters and the marsh interior. So with these three methods together, we can track the emergence and influence of levees across temporal scales. And this, the first two here were recently accepted into Communications, Earth, and Environment. That's chapter 1, and they should be published, the findings there, in a month or two. So feel free to look at those if you are interested. So chapter 1, we track marsh evolution in 2 divergent coastal plain watersheds. So these are 2 of the 12 that have been looked at previously. We wanted to look at them in richer detail to see when a estuary is deforested, which is the Oyster Creek watershed here. How quickly does a levee emerge? Does it emerge? Is our hypothesis true that the edge will grow more rapidly than the interior? And compare that with the conserved watershed, which I'll show in green for the rest of this talk. So we have the deforested red watershed and the green watershed, Gales Creek, that is conserved. And here we are at UNC IMS today. So we're sort of in the middle of these 2 watersheds, both pretty small, around 10 to 15 square kilometers, but well connected. The land use change is well connected to downstream supplies. And other studies have shown that in subtidal regions. So here's what these watersheds look like from 1959 to 2020. First at the deforested watershed on top. In 1959, it was mostly forested, but by 2020, you can see about 50% of the watershed, especially in the headwaters, has been cut down due to silviculture operations. That's tree harvesting associated with the Open Grounds Farm, which is actually the largest continuous farm in the United States, right nearby us. Whereas at the conserved watershed, there was selective logging happening in the 1950s, but by 2020, due to a Land Conservation Act, that watershed had reforested predominantly. There was some development along the margins, but not very close to the headwaters that we think are feeding down into our marsh systems, which are blown up from these little arrows here. And these are actual measured, oh, hello. These are actual measured transects of marsh elevation and where we took the cores at these divergent sites, one that is sediment loaded and deforested, one that is recovered, Gales Creek, and conserved.
Recording in progress.
Oh, no. Should I change anything up here?
I think we're good.
So we use sediment cores in these systems. That was our first method of getting at how levees emerge. And we use these to recreate depositional histories across the marsh platform using a naturally occurring radioisotope called lead-210, which is attached to the marsh sediments. It occurs in the water, it occurs atmosphere. Well, it gets in the atmosphere, it falls out into the water column and attaches to the sediment. So we take these cores in the marsh, again at 2 meters, 8 meters, and 15 meters from the edge. We bring them back to the lab, and like a push pop, we extrude them and cut them centimeter by centimeter into these little patties. So we cut them down to 50 centimeters depth at each of these 6 cores, so 3 in each watershed. And then we concentrate the radioactive signal using an acid digestion technique onto these little metal planchets. We then count those planchets for 24 hours in an alpha decay detector, which tells us how radioactive they are. And any deviations from the expected exponential decay of radioactivity with depth tells us something about how rapidly that material was put down. And we use the constant flux, constant rate of supply method for folks who are interested or know about lead-210, which allows us to resolve with every centimeter pretty high resolution sedimentation rates going back in time. So every centimeter we know how fast it was put down, plus or minus a small rate. So at the deforested site, we had 10 years of, or 10 distinct land use classifications from 1959 to 2020, not just the beginning and end that I showed. And what we see with more detail here with a finer tooth comb is that for quite some time, there was no change in this watershed. And then we saw rapid deforestation. Here in yellow, that's the beginning of the silviculture operation. So from the 1990s to 2000s, about half of the watershed was cut down. So that's a massive change in a very short period of time. And we wanted to observe how that changed sediment accumulation rates, which I'll show on the upper axis here, through time. So we've changed depth now into time on the vertical axis. So at the edge, that sediment core taken directly at the edge, we see sort of a slow increase through time and then really rapid sedimentation up to 12 millimeters per year at the edge of our salt marsh there. And in about 15 years, the marsh accreted 13 centimeters. So in an area that has a tidal range of 32 centimeters, that represents a really large bounding up in pretty high in the watershed, or in the water column. And it rose so high that we think it no longer was getting inundated frequently enough to continue sedimentation. So it reduced towards present. Let's look at what happens directly behind it at the middle site. So precisely, we see a little increase following deforestation, but precisely at the time when the marsh edge was accreting most rapidly, the middle showed the slowest sediment accumulation rates of any time in the past 20 years. While the interior location also showed a lull from 2000 to 2010. And so this is a very close spatial trend where we see directionally opposite trends in sedimentation at the deforested watershed. This suggests to us the sort of emergent levee that forms following sediment loading. And here, putting that all together, we have rapid deforestation leading to the edge sediment loading and a slow rollover through time, and then land stabilization towards present and accretion rates that begin to look more common across the marsh because the edge is just so high in the tidal frame. And we can compare this with the conserved watershed where we expect no sediment loading. So now I'm showing all three from the edge in black, middle and interior, which are sort of indistinguishable at this site. We see the reforestation through time in green, where about 40% of the watershed turned to 60% reforested, and the development did happen on the margins, but we don't presume added much sediment to the system. And this is the signal, we think, of edge rollover, where the fixed coring locations that exist on the marsh are moving closer due to edge erosion to the sediment-laden waters. So because of that process, they're accreting more rapidly with time simply by being closer to the water that delivers that sediment onto the marsh platform. We believe this is happening at both sites, but with the added sediment loading story at the deforested site. Now we can look from 2001, which is here, that line I draw, that's sort of after land use change in the deforested watershed. And we can compare sediment accumulation rates at the edge there, or the levee, with what's happening directly behind them in the middle. And we see a negative correlation between high sedimentation rates at the edge and lower rates at the middle directly behind it, which suggests to us that the accretionary levee is growing at the immediate detriment to the marsh behind it. So when the levee increases, we see directionally opposite responses at the middle and interior sites for that sediment loading period. While at the conserved site, when one increases, so too does the middle, so too does the interior, just at lesser rates. And this is more what we would expect for a marsh in equilibrium, where the edge is generally accreting faster, but directionally in the same way as the interior or middle sites. So we can put this all together and compare sedimentation rates with sea level rise before and after land use change. Here on the y-axis, I'm showing sediment accumulation rates, SARs. Those are these color bars from 1953 to 2001 and 2001 to 2021. And sea level rise, which is in blue here with 95% confidence intervals for both of these plots. Before the land use change and when sea level rise was lower, around 2 to 3 millimeters per year, all the marshes were keeping up with that rate of sea level rise. But come the very high rates that we've seen in the past 20 years and after land use change, only the edge of the 6 cores that we took for this study, only the edge in the sediment loaded system is keeping up with modern rates of sea level rise. So that suggests to us that the interior may drown if we are expecting, really high rates of sea level rise to continue and to remain elevated. So a potential management implication here is that folks who are using thin layer placement, this is a beneficial reuse project where sediment is dredged and spread across the marsh, can maybe find areas that aren't near the edge that have a low capacity to receive sediment and distribute that material towards the interior of the marsh and help that elevation compete with sea level rise or get marshes to an area where they aren't on the trajectory of drowning. So these sediment cores that we took across these sites with divergent land use change showed rapid levee emergence following fluvial sediment loading at the deforested watershed. And now we can look at remote sensing of shoreline erosion to see how much that shoreline is moving back and how much extra sediment is being added to the system from local erosion. This was work that was helped by Lillian Cooper, who came out for a summer and delineated shorelines from 10 dates, or at 10 dates from 1959 to 2022. And these are the same dates that we have land use classified as well. So she helped using automated and manual methods of shoreline delineation to say where this margin was, this shoreline, over those 10 years or 10 distinct dates. Then we calculated shoreline erosion rates along in this watershed about 1,500 transects, they're spaced every 5 meters, to see how rapidly the shoreline is eroding. We multiplied scarp elevations along each of those transects to see how much the vertical amount of material that was being eroded with each meter of shoreline erosion. And then we multiplied that finally by edge sediment densities taken from our sediment cores at each of these sites to find shoreline mass flux rates, which are measured in kilograms of sediment being added for every meter of shoreline per year. So how much mass is coming off locally? And just briefly, we found that there was lower edge-derived sediment supply at the deforested site, which enabled the prominent upstream deforestation signal that we saw at that site, because the local sourcing from edge erosion simply wasn't that dominant in this watershed. In fact, there was a third as much material coming off of the edge at the deforested watershed, 6.8 as compared to 20, as was at the conserved watershed. So the signal was really prominently recorded here in the deforested watershed, disproportionately than that area that has a lot of local supply, which is the conserved watershed. And later I'll get into some of the water column measurements, but we'll see reflected in the present day that we have higher suspended sediment concentrations at the conserved watershed, I think because of this shoreline erosion. And so I'll move into that now. This is chapter 2 here. So the chapters are sort of out of order. I went from chapter 3 to chapter 1 and 2, but this will be the last chapter I talk about. And here, after we've shown that these levees emerge in the watershed, and we've shown that there's erosion of a shoreline that adds extra sediment, we now know that there's fluvial sourcing of material from the landscape, runoff from deforestation, from the watershed. We also know that there's this added material coming from shoreline erosion. All of this is mixing together in the present day water column, and at high tide, that water floods into the marsh platform, and we can observe directly how that sediment decays across the platform and whether or not levees of different morphologies relate to that decay. So that sort of gets us at the process of cross-shore transport. We know that it emerged historically from our sediment cores, but what's happening on individual tidal timescales that could tie back to the emergence of these levees? And the sensors we'll use help us get at that question. And there's been some good foundational work on similar topics. Folks have found a relation in 2001, Friedrichs and Perry, find a relation between sediment concentrations in the creek and deposition on the marsh platform. So when you add sediment to the water column, you expect the marsh that at high tide is flooded should see some of that sediment. And I'm skipping a lot of work in between here, but these are some core papers. In 2003, Temmerman et al. Show that deposition from suspended sediment concentrations measured in the water column aren't evenly distributed in space. So with distance moving away from the marsh edge, you see lower concentrations or lower estimates of deposition falling out of the water column. And this is what gives birth to the levee. So this isn't totally surprising, but this was measured from direct water column measurements of seeing what's floating around in the water. And then in 2020, Coleman et al., as part of Matt Kerwin's group, found that interior sediment supply is decoupled from the channel even on short distances. So we can add a bunch of sediment to the water column, but it doesn't always reach the marsh interior. And so why is that? That's where our question is getting at how levees moderate that sediment connectivity. Because folks really haven't asked, what role do levees play in moderating the connection between that sediment-laden water and the sediment-deprived marsh interior on short timescales? And also, can we use observations of sediment in the water column to sort of refine our empirical models that try to predict how marshes evolve through time? Because right now, there's generally an application of a single cross-shore gradient in suspended sediment decline, that's not as sensitive to water levels or what's in the channel water column to begin with. And so we're hoping to refine that as well. So here I'll use the same watersheds, red for Oyster Creek, green for Gales Creek, and a new yellow color for Wards Creek. This is an additional watershed here that has a distinct levee morphology because we wanted to characterize a variety of these levees and see how sediment decays across these distinct profiles. Here's where we installed the sensors, 4 of them at each site, in a cross-shore transect, starting in the channel and moving into the marsh in a shore normal direction, so perpendicular to the shoreline. And our hypothesis here is that larger levees in the present day reflect stronger cross-shore attenuation of suspended sediment. So with a larger levee, we expect that material will more rapidly decay into the marsh interior, and these levees either result from that decay or are moderating or causing that decay. And so we look at these 3 distinct sites. First is Wards Creek here with a very broad levee. You can see how wide it is. It covers 2 of the sensors in the way we arranged these sensors on the platform. And it has a 10% relative prominence, which we define as the height of the levee compared to the difference between mean high water, shown as these lines here, yellow for Wards Creek, and mean low water. So this is essentially how high that levee sticks up into the water column when it's flooded. And it's some way to scale between sites with different tidal range. At Oyster Creek here, that's the sediment loaded site where we saw the emergence of the levee. We have a very high levee that has a 32% relative prominence. So it makes up 32% of the mean tidal range there, sitting pretty prominently in the water in that tidal range. And then at Gales Creek, we have the smallest levee of all here. It's quite narrow and takes up a 10% relative prominence between mean low water and high water. And now we can use these sensors that I've been alluding to. These are optical backscatter sensors, which emit light into the water column and predict or measure how much of that light is backscattered off of sediment that's floating in the water column. And there's a directly proportional response where the more light that is reflected into the detector, the more sediment is in the water column. And so in this schematic, I'm showing lots of sediment in the channel, a lot of dots here, and fewer dots in the marsh interior. So these measures are at the same, or these sensors are measuring totally different concentrations at the exact same time on a high tide. And I'll call this a high tide event. So when I'm saying a high tide or flood event, I don't mean like a big storm. I just mean water levels getting onto the marsh platform. And again, our sensors are oriented in a cross-shore dimension, 2 meters away from the edge, 2 meters into the marsh, 8 meters, and 15 meters. And these are just 4 sensors, which do a pretty good job of resolving spatial decay. But we were also interested in using more sensors originally. And so one summer, David Go came out and helped build 20 or so of these open OBS, open source optical backscatter sensors, which are much lower cost than commercial varieties. This was a project started by Ted Langhorst here and a committee member of mine, Emily Idem. And the goal here was to have richer spatial transects of these sensors. They performed quite well for a limited time. So here's some of the data from those sensors in a cross-marsh orientation. I won't get into it too much. But because of fouling in these waters, because these waters are so bioactive and films grow on the sensor face, within a pretty short amount of time, the signal from these sensors was degraded. And so we stuck with commercial sensors on the left here, the RBR Duo, which came equipped with wipers. And my old undergrad advisor, Matt Kerwin, helped loan these, so I'm really grateful for him coming in clutch and saving the study here. So these wipers go off every 15 minutes and wipe the sensor face clean. You can see how important that might be in the open channel, where after a month of deployment, there's a lot of algal growth and even barnacles on these sensors. And because these are optical measurements, those would totally disturb the values we measure. So we installed these sensors across the marsh for 1 to 2 month deployments at those 3 distinct levied morphologies. You can see them moving into the marsh interior here. We put them at 6 centimeters above the marsh surface. So that's an area where we can capture as much of the flood as possible, but not being too close to the bed where there's any interaction of light scattering off the ground. We also put tiles in front of them to prevent vegetation from interacting with the measurements. And so here's that schematic again, from left to right. We're at high tide, waters are on the marsh platform. And I'll show suspended sediment concentrations when this marsh is inundated, like in this image. But now I'll turn this transect on its side, and we'll be looking at the transect in a vertical dimension. So now we have moving from the channel to the levee, on top of the levee, interior 1 and interior 2 sites. And what I'm plotting here is a whole month of data at Gales Creek. On the bottom, water levels are shown. These sensors also take measurements of how deep the water is at each sensor. And suspended sediment concentrations, anytime the marsh is inundated, are shown via this color bar from 1 to 100. It's on a log scale. Dark colors here represent really turbid, really sediment-laden water. Areas that are gray are when the marsh is dry and there's no water on the platform. For parts of the month, there's only 1 flood per day. That's because the tides were pretty low during this time. But then late in this deployment, we saw really high tides, where twice a day the marsh was flooded for a pretty long duration. And so I'll zoom into 2 of those days to talk about the signal in more detail. So we're using the same color bar here from 1 to 100 milligrams per liter, moving from the channel to the marsh interior. This is a single high tide event I'll focus on. So there's a variety of, or there's 4 high tide events, but we'll just focus on this one on the left. You might notice that concentrations are highest in the channel and decline with distance into the marsh platform. Each of these small bars here is a 10-minute median of the the measurements we took every minute with these sensors. So we median them to smooth it a bit and then display them stacked next to each other. So a decline across the marsh in the lateral dimension, that's material that's not reaching the marsh interior that is in the channel. But we also see a temporal decay with higher suspended sediment concentrations in the beginning of the flood and lower at the end of the flood. And we interpret this as sediment deposition. So this is really cool for me because we get to see on a single tidal flooding how sediment is falling out of the water column and relating to those long-term depositional signals we saw with the sediment cores on decadal bases. So this is just a few hours of flooding that's incrementally driving sediment onto the marsh platform. And we can take averages. So there's a lot of nuance in these signals. Not all days look so clean like that. And certainly there's interesting questions to be asked on individual floods. But for the large story, I think it's nice to look at averages across the entire deployment to see what's coming and what's going from this marsh. And so that's what we're looking at here, where across the entire deployment, suspended sediment concentrations decay across the marsh. So here's our marsh schematic again. Suspended sediment concentrations are shown on the y-axis. And we see the decay from higher concentrations in the channel to lower concentrations in the marsh platform. And we'll quantify this in a moment. But we also see that temporal decay, where suspended sediment concentrations are higher during rising tides, on the left here, the darker color, than on falling tides. And this arrow here shows the movement of median concentrations from the rising tide to falling tide. So that distinct amount of sediment we presume to be material that's falling out of the water column onto the marsh platform between these 2 tides. So this is across the entire 1 or 2 month deployment, depending on the site. Significant differences using a Mann-Whitney U-test are indicated with these 2 asterisks here. And significance at the p less than 0.01 level is 2 asterisks, 0.05 is 1 asterisk. So that's just one site. Oh. At Gales Creek, we see a similar trend. Decay with time, so higher sediment coming in than is going out, and also decay across the marsh. And at Oyster Creek, we see the highest concentrations actually on the levee, which might add up to the story of why we see such high deposition on the levee there and the emergence of it. And due to the shorter deployment duration here and less frequent flooding, we don't see significant differences between the rising and falling tides. Well, we can fit functions to this cross-marsh decline and suspended sediment concentrations that get us at sort of a decline value that could be fed into models of marsh evolution to say how sediment from the channel is linked to the marsh interior. And the function looks something like this, where concentration at a location on the marsh X decays exponentially with distance into the marsh. Distance, again, being X, relative to some decay coefficient K. And it starts from some concentration on top of the levee here. So the higher the concentration, the more material to work with, but that decay coefficient tells us how quickly we lose it moving into the marsh. Here again is suspended sediment concentrations on the y-axis, moving from left to right across the marsh platform. And anytime the marsh was flooded, for each minute measurement, we would look at a decay rate across the marsh platform. And here I show the averages of those and the 95% confidence intervals. And this is on the data set with temporal autocorrelation removed because we have measurements every minute. So a lot of them look quite similar and we need to remove the autocorrelation there. And these compare quite well. They range from 0.013 to 0.036. Compare quite well to values that are used, singular values that are used in models, but we can see even between sites, there's quite a bit of variability in these K values. And to make it a bit more intuitive, this K value, a K value of 0.03, for example, means that for every meter you move into the marsh, you lose 3% of the remaining sediment that's in the water column. And what we find is that across sites with larger levees, Wards Creek and Oyster Creek, we have steeper decays. So more of that material that was present on the edge no longer remains by the time you get to in the water column by the time you get to the marsh interior. And so that decay tells us something about levee emergence, either that these levees are responsible for this decay or that these levees are the result of this decay. So it's sort of a chicken and egg question that we can't mechanistically get at with this data, but I think it's pretty important if we're trying to integrate the capacity of levees to be related to this cross-shore gradient and to interior sedimentation. So that's the lateral decay with distance into the marsh. We can ask how this lateral decay varies with sediment availability. So if we add a bunch of sediment to the system via deforestation or via dam removal or mining in some watersheds, mining in the south is really important in adding sediment to the water. And with additional sediment in the water column, so higher channel suspended sediment concentrations, we see an increase in that K value, meaning that material has a lower capacity to reach the marsh interior. Disproportionately, it remains at the edge of the marsh. We see significant relationships at both Gales Creek in green and Oyster Creek in maroon, and not as much at Wards Creek where we have the broad levee for this metric. These lines also, I should say, are the Thiel-Sen estimator, which is robust to outliers, and significance is indicated with the Spearman's correlation coefficient. And these were also done with temporal autocorrelation removed. So added sediment is disproportionately ending up on the edge of the marsh. These K values say that you load a bunch of sediment, it doesn't reach the marsh interior. So this is the exact process of the levee emerging after deforestation or after sediment loading. While with flood magnitude, if we have really deep waters, for example, at a spring tide or a king tide that brings water really high onto the marsh platform, we sort of overwhelm the capacity of a levee or vegetation to restrict sediment flow. And so with really high water levels, the cross-shore decay declines, almost to zero in some cases, where sediment concentrations that are measured across the marsh are equal at the edge as they are in the interior. And so this might mean that with increasing sea level rise, if these marshes are keeping pace, there's a bit of a negative feedback where sediment actually has an easier time reaching the marsh interior. And whether or not that, that added sediment offsets the fact that these marshes are inundated under such underwater so frequently that they begin to drown and the plants die off, that's unclear. I think that's an avenue for further study, but there is some negative feedback here where sediment is reaching deeper into the marsh. I think it's quite striking how similar the relationship is between sites, though the intercepts are different. So those were all relating lateral decay and suspended sediment to what's in the water column, to how deep the water is. But as I showed in when we zoomed into this image, there's also this temporal decay, which we think is water falling out directly in the water column, or sediment falling out in the water column directly onto the marsh. And this follows a function of the same form. Concentration at time, T, is related to initial concentration at the beginning of slack water, highlighted here, decaying with some lambda decay coefficient. So we define slack water as 30 minutes before and after peak high tide. And then this lambda is telling us how much of the sediment is falling out of the water column during that time. And we chose this period because we assume that there's no lateral advection of new water onto the marsh. Water velocities are minimized. And so this is a good chance to look at what's actually precipitating out of the water onto the marsh. And now, so this is a single flood event. We observe a lot of flood events for our deployments, our month or two long deployments. Here, anywhere from 30 to 40 events, depending on where we were at on the marsh, because they're sitting at different elevations. And predominantly, for these slack tides, we're seeing decay in suspended sediment concentrations. So mostly, at most of those events, materials falling out of the water. There are some that don't abide by that assumption that we could look into in the future, but predominantly the signal is material falling out of the water. We can then use these lambda decay values and using a mass balance from Krohn back in 1962, multiply it by water depth that's sitting over these sensors. Remember, we have measurements at each of these sensors of how deep the water is to get an effective settling velocity. So how rapidly the sediment is falling through the water column onto the marsh platform. And we do this to help us estimate present day deposition, to link together what's in the water column with what we found in the sediment cores. And we do that by multiplying those settling velocities with concentration in the water column. And then we scale, so that gets us into grams of sediment for every meter squared per hour. How much mass is falling out of the water while these marshes are flooded. We can then scale that by how many hours in a whole year we expect the marsh to be inundated to get at deposition on a yearly timescale. And that's what I show here, where we estimate similar mass accumulation rates from the water column as we find in the top of our sediment cores at Gales Creek. So estimated just directly from the water column, what's settling out of it, scaled from a month to a year, we have a value of about 0.184 grams of sediment for every little square centimeter on the marsh per year. That's our estimate from the water column. What we observe in our sediment cores at the exact same site is a value of 0.205 grams of sediment for every centimeter squared per year. And so when we look at the ratio of these two values together, it's 0.9. And so we see at Gales Creek, we do quite well just using what's in the water column at estimating long-term deposition rates. So this is pretty exciting for managers who might want to put these sensors out and find out how well they characterize long-term deposition. But at Oyster Creek and Wards Creek, we don't see the same trend. We see a kind of a vast underestimate. It's around 0.1 to 0.2, the rate we estimate from the water column versus what we see in the long-term deposition record. And we believe this is because Gales Creek sat lower in the tidal frame and was inundated for anywhere from 30 to 45% of our deployments, while at Oyster Creek and Wards Creek, inundation durations were between 6 and 14%. So we think we just missed a lot of the important flooding events that would be bringing sediment deep into the marsh interior. And so these estimates don't characterize sedimentation that well there. So for managers who are trying to use this type of measurement, maybe the height of a marsh within the tidal frame can inform how long you put out a turbidity sensor to characterize sediment transport. And also, I think this reinforces that we need measurements deep in the interior because the channel isn't always a good estimator of what's reaching deep into the marsh. So I want to move out to some takeaways from the Marsh chapters. I won't talk about the takeaways from the Barrier Island work, but those are there published if you'd like to look at them. The first finding from chapter 2 is that levees correspond to higher cross-shore sediment attenuation on tidal scales. And so nature-based solutions like living shorelines or shoreline hardening that plan to prevent shoreline erosion should consider the fact that levees might have this capacity to moderate interior sediment supply. And so with a levee or with a nature-based solution at the edge, a living shoreline trying to lock in that position, we might actually be doing a detriment to the marsh interior. And so we should consider elevational distributions before going out and installing these willy-nilly. The next finding from chapter 1 was that deforestation drove rapid sedimentation on the marsh edge. And this raised levee prominence and lowered connectivity in the immediate period after levee emergence. We saw that with the sediment cores. And so efforts to enhance sediment loads, such as dam removal, which has been proposed to restore sediment flows to downstream ecosystems, won't evenly benefit marsh platforms and might even make these suboptimal edge morphologies where an emergent levee restricts cross-shore flow. And again, this effort of thin layer placement where sediment is spread across the platform could actually remediate some of this by giving us more optimal elevational distributions on the marsh interior and preventing that levee from impounding water behind it. And then we used some inundation analyses, both with the water column measurements of how frequently these marshes were inundated and from our sediment cores to show that prominent natural levees reroute flow and deflect it away from the marsh interior, making it travel more circuitous paths to reach the interior marsh. And so efforts like runnels, where levees are breached and cut through, might restore some sediment connectivity to the deep interior, and also could drain marshes that are impounded and have a poor, have waterlogging that's leading to ponding in those areas. And so to put this together, in submerging marshes, we expect that the edges will survive, perhaps at the cost of or in a distinct direction from the marsh interiors. So our marsh interiors will begin to drown, not keeping up with sea level rise, but the edges will survive. And so to relate this back to the sea level rise viewer, where we see sort of a lateral movement of marsh with time, sort of just eating away deeper and deeper into the land, we expect that actually the edges will be surviving and the marsh interiors will no longer be surviving. And this recently has been given the nice title of the donutification of marshes, where the edge remains nice and healthy and fluffy, but the interior is a hole. So I think there's more chance to bring microtopography, this idea of small elevational differences, into the marsh story to see how it moderates resilience with sea level rise. Because on this very flat coastal plain which we exist within, a little bit of elevation goes a very long way. So that's all I have for the talk. I'd like to thank my advisor, Tony Rodriguez, who's been such a wonderful mentor this whole time and has always joined us in the field and been a great example of how to kind of lead a lab by example, an example of an example. As well as my lab members, Eve and Yasmin and Molly, who published a lot of the foundational work for this, Naomi, who's helped out, as well as my committee, Brent McKee, who's on main campus, Tamlin on main campus, Emily Item, and Ellen Herbert. Emily's over at Oregon State now, and Ellen is with Ducks Unlimited. So thanks for sort of steering my inquiries and helping me find the papers that are so useful to kind of help me know where to look and where not to look, and what holes are not the right ones to dive into. And then also thanks to the IMS community, who's been such a warm place. Here we are at the 75th reunion. There's a whole bunch of us. It's been a really warm community. I think you can tell by all the food folks are bringing and the smiling faces in this room. I've loved being here and having such great access to the coast and to my field research areas. Also, thanks to the support staff, so Ryan Neve, our tech wizard, and Dina, and Jess Phillips, Phil Herbert, Stacy Davis, Jim and Jimmy, and Nina as well, for keeping the lights on and keeping everything running here. I also want to thank Matt Kerwin. There's a slide here. Yeah. I want to thank Matt Kerwin and Orencio Duran. Matt is who I worked with during undergrad and loaned those sensors. And both of them have given me sort of great direction in my science, and I've really looked up to them in the way they ask questions about coastal ecogeomorphology and coastal systems, and sort of how we view sea level rise as setting the evolution of our landscape. Also, thanks to William and Mary Geology, who gave me, I think, a really nice foundational understanding of and appreciation of geology, and just such a fun group to be with. Here we are in Norway on a field course. Also, the NSF Advanced Studies Institute, which I was lucky enough to take part in France, where we looked at coastal hazards. Let's Talk About Water, who's a group that's done a tremendous amount of work trying to get science films into the public media using short film exposés where science is shown via very, very short films and using short film competitions. As well as Siren Coast, where the goal has been to get our science into K through 12 lesson plans. That was originally started by Justin Ridge here, who's also a former member of the Rodriguez Lab. And that's been a really lovely community to interact with teachers in the area and ideally get more young scientists excited. And then finally, well, not finally, second to finally, my friends, I've made a lot of friends these past 5 years, and you've all been such a lovely part of this experience. I think a PhD can actually be fun, and I've learned that. I didn't know that at the beginning, but it's been a wonderful time. Mark and Nick, who are my lovely roommates, I'm so glad we found each other here in the bottom, as well as my friends from home, who I really look forward to celebrating with, and friends from Eames up on main campus, my Peace Corps friends, and my original house that I lived with during the pandemic. It was just 6 of us all together in a little house, so we kept each other company, and I'm glad we had all of us. And then finally, my family, my dad and mom, my brother and Trang, his wife, as well as Aviva, the budding scientist here. It's been a lot of fun. I always know I have a great place to come home to, and we make the most, I think, of every day when we're together. And I love you guys. Thank you so much for being here. So I appreciate it. And of course, to my brother and I, who have given each other several high-quality haircuts over these past 5 years, I think we've got a bright future ahead. Yeah,
We should celebrate.
and of course, Lee as well. We should celebrate again. And so with that, I want to welcome any questions and thank everyone for coming. Yeah. So if you just raise your hands, I can.
People online, if you virtually raise your hand, I can unmute you and you can ask your question.
Yes,
I have a
Rachel.
question. What's special about 2, 7, or 8, and 15? So what's special about the distances and how are those
Yeah.
kind of selected over the course of your,
Mhm.
and how might shifting any of those points change anything that you've found?
Yeah, so it's a really good question because, right, there's this spatial decay, and depending on where you look on the marsh, you might get a different signal, which is what I showed with the levee emergence. We chose those locations based on the 2020 Coleman et al. Paper, which found that across those distances, that's when we begin to lose the sediment signal, and when it starts to look like in the marsh interior, when it begins to look, it's essentially a flatline sediment supply. And so we see most of the decay within the first 20 meters of the marsh in microtidal marshes. If you were to go to a marsh that had a tidal range of 3 meters, for example, you might want to space that out a bit more. But most of the interesting story is in that immediate 20 meters. And so there's some good literature that has shown that that's sort of the ideal area to target, especially if using these turbidity sensors to get at that decay profile. Yeah.
And I guess similarly, like question 1B, you talked about +2 for your levee.
Mm-hmm.
What would be is there something magical there about whether you really went right for the edge?
Yeah.
Right where the water's coming up. There's often
Right,
like
right.
if you go out fishing around here, you kind of see like this, almost like this lip that forms. And I just wonder,
like undercutting?
yeah, it's kind of like undercutting, but then
Yeah.
there's the levee, but then the water kind of tops over it. I just wondered a little
Yeah.
more, like, has there been any micro scale work over like the right at the edge and the 0, 1, and 2? I'm talking about the
There-
+2 that's
Right.
right there at the
I'm not familiar with it. I mean, this is, as far as sediment coring efforts go, some would call this insane, because these are a lot of sediment cores that take a large amount of work to work up on a very short spatial scale. I don't know anyone who's done it on the order of
Even
0 and
finer
1 and 2
scale.
meters.
Yeah.
But the reason we avoided directly at the edge is because there's a lot of bioturbation in these marshes. If folks have been out, there's these crabs that dig around. And so we don't want a sediment core that looks like Swiss cheese. That would disturb our lead-to-10 profiles. And so we found via some exploratory coring that moving 2 meters away minimize that bioturbation issue.
Great, thank you.
Yeah, Joel.
So I did want to say publicly that for the last 3 or 4 years, when I've seen in the hallway, I always think this is interesting and fun. Whether it's photography or dumpster diving. So you're a very good fellow. Don't change. I wish I was more like you.
Oh,
But I'm not, so now I want to attack. So I want to understand, because it's interesting, because I may have missed this earlier in some earlier work, but in 2007, there was a massive cutting of trees in Gales Creek.
Oh, really?
If you go look at the maps from 2006, 2007, on the western side, I think there's like a couple hundred acres, 100 acres or something. It's
Yeah.
like a fourth or a fifth or a sixth of the watershed.
Okay.
So
Was it in the lower watershed or?
it's it's kind of in the lower going up to the maybe halfway, up that stem that kind of goes. So that happened.
That could be contributing to that
But
edge
yeah,
signal.
your data are what your data are.
Yeah.
You don't see. So if you accept the premise that that did happen, you can check it. I mean, it's,
Yeah.
you can look at like Google Earth time lapse.
Mhm.
It's there.
Yeah.
And in fact, we got contacted IMS by residents of Gales Creek because they were worried about sediment loading from that. So given that that happened, is there a way that you could still like explain why your data look the way they look with no berm? Is there something that could explain that?
So
Size of the watershed or the ratio of what got cut or where it got cut?
I think a couple of things could explain it. So we do see that levee started creating a good bit faster. We chopped, in the last 20 years, that was that. Let's see, I'll pull that up here. So on the right, we see, maybe we're seeing some of that here. I haven't looked into each of these years of the classification. These were published, and so I sort of take them as is. But we do see following, I guess, 2007, if that's where that land clearing was, an increase through time. We chalk that up to edge rollover. There's a chance that added sediment is ending up on the edge. Also, because this marsh sits lower in the tidal frame, it's about at mean tide level. I could expect that and because we do see with our turbidity measurements, there's better cross-shore connectivity. So more of that material might be ending up in the marsh interior and contributing to those increasing rates where we don't see a divergence at the edge from the marsh interior. So yeah, with the increased.
Remind me where your cores were in Gales Creek.
They are here. If you see where these arrows point to, about halfway down in the estuary, which we try to be common across both sites, and also informed from the past sediment cores we had in these watersheds. So where was this land? Was it that area up here?
No, it's like, they went like to the water's edge. So like Gales Creek, take that western shoreline.
Mm-hmm.
All of that got cut in 2006 or 7. Go up a ways.
Yeah.
To there, go all the way to the road, go to Highway 24.
Okay. So 24 down here.
Yeah. All that got cut away. And so maybe your core was high enough up.
Yeah.
This little.
Well, it's actually at mean tide level. It's one of the lower cores.
I mean,
But,
check that.
yeah, but right. It could have been upstream of that signal. So there's some tidal oscillation that would have potentially resuspended it. Yeah, I should go back and this imagery underneath, it's black and white, but it's actually from 2020. This is NAIP imagery, which has high resolution, and it looks like it's revegetated by that time, but
To the naked eye, like within 5 years,
it came back.
trees were back. So
Yeah.
maybe something about the recovery time.
Yeah. I don't know. I'd like to look into
Yeah,
that.
look it up.
Cool. Yeah, Rick.
So if you had a marsh that didn't have a levee,
Mhm.
what would you expect the lateral sediment profile to look like in waterfall?
I think there would be less bed form drag because the levee's sitting proportionally lower, or there's no levee. The water levels are deeper, and so there's less of that bed shear. But we still have vegetation, and so that is baffling flow and would lead to some cross-shore decay. So I would expect that. The presumption here is that there would be less drag without the emergent levee, and we would see a lower cross-shore decay in suspended sediment with no levee.
So the resulting cross-shore sediment profile
Mhm.
would in fact lend itself to creating the levee.
Can you ask that again? Sorry.
If you have more sediment close to the channel and less sediment further away, is this a causal mechanism for the levee?
Yeah, exactly. That's how levees form in fluvial systems and rivers. Most folks think of levees and probably think of man-made levees that are, in the Mississippi River and try to constrain flow, but they naturally occur anytime water spills out onto the floodplain, in this case, the salt marsh. So yeah, we expect the levee to exist. Sometimes they don't on sort of passive marshes that fan out into the water, or any marshes where there's undercutting and the levee slumps down due to if it's a high enough marsh scarp.
And so when the water goes over the levee,
Mhm.
it must speed up.
If flows are shallow, there is a surge. Under very shallow waters, there's a surge of velocity, but it's a larger cross-sectional area, so I don't think it speeds up on a broad scale.
Well, if it goes down,
Oh, you mean like because of the elevational difference?
well,
It depends on water head.
cross-sectional area. On top of the levee, you have simply a smaller.
Cross-sectional area.
Than.
Yes. Yeah, so a lot of
So
studies
is
have
the
shown
levee
that it's
actually reinforcing the sedimentation profile, or is it actually tending to level the sedimentation, allow
Right,
sedimentation?
right, by constricting flow and pushing it deeper. I mean, I think our observational data suggests that sort of narrowing of flow doesn't increase velocities enough to push that sediment that far into the marsh. And I think there's a decent amount of work with Spartina alterniflora in this vegetation that shows velocities are quite low on the platform once the marsh is flooded. And there's like similar rates of turbulence across the marsh as well, which can keep that sediment in suspension. Yes, Brother Dan.
Yeah, first I want to say great work, and the double-breasted violin plot was amazing.
Oh, good. My brother's a data scientist, so he likes
But a question I had, so it seems like a lot of these sampling periods with the accretion of the sediment are during the normal course of operations. It was a surprise to me, actually, that not every high tide necessarily floods these, and either there's seasonality or different variation. But what percent of the accretion occurs during this sort of normal tide-dependent phenomenon versus the extreme storm events? I mean, how much is just not being looked at here because it's from some extreme, very short-term event? So
a study came out recently that showed 5% of the inundations can drive like 45% of the sedimentation. So your intuition is exactly right. It sort of follows a power law distribution. That's also why we think the sites that were sitting higher in the tidal frame that only were inundated 6 to 15% of the time didn't scale as well to annual timescales, because we just missed a lot of flood events. And so Gales Creek here is the lowest, and we see a lot of flooding. But actually the other sites, there's much bigger gray gaps where we don't see that flooding. And so in an ideal world, we would have these sensors out to capture those events. And I was really hoping to see a really big sediment transport event. Just based on the months we put them out and the systems we're in, we didn't see that. But folks do put them out for longer and try to quantify the extremes and can look, show that that's a pretty big part of the story as well. But the background humdrum sedimentation is also cumulatively adding to that. Yeah.
We can do one more question if there is one. If not, we can move to the.
Sure.
Oh my gosh.
Heather?
It's just me.
Heather.
It's just me. I mean, this might expose my lack of experience in marshes, but if one goes full donut, what does that center look like? Is it just mud? Does the marsh still kind of exist there?
It's like a mud flat, patchy vegetation, some pluff mud, so it's like really, you sink in super deep.
Oh.
At really high tides with enough energy, that sediment can get scoured out. There's no more roots holding it together. And so you can develop interior ponds, which then if they get large enough to hold water, they can have fetch, and you can have wind-driven waves eroding from the inside the marsh platform. So some of the work I did at Blackwater National Wildlife Refuge in my undergrad looked at these ponds and how they grow, the mechanisms of growth, and when they get big enough, what they might do to the marsh from the inside.
Cool.
So yeah,
Thank you.
they're there.
All right, Josh.
Yeah.
10 minutes.
Yeah, I'm gonna do.
And then we'll meet in the other room.